Hello and welcome to The Explainer. Today, we're diving into some really cool technology at the heart of the climate fight. So, what if we could actually reverse a smokestack? I mean, what if we could take carbon dioxide, which is, our planet's #1 waste product, and turn it into the very things we need, like fuels, plastics, and all sorts of essential chemicals? It kind of sounds like alchemy, right? But it's the very real science behind something called CO₂ electrolysis. Let's get into it. So what's the catch? Why aren't we doing this everywhere already? Well, the problem is that CO₂ is, for lack of a better word, happy. It's an incredibly stable, low-energy molecule. Its atoms are locked in these really strong bonds, and it just doesn't want to break apart. And that stability is exactly why it hangs around in our atmosphere for so long.
And that right there is the fundamental challenge, the carbon conversion problem. If you want to turn CO₂ into something new and useful, you first have to convince this stubborn molecule to react. And, as you can imagine, that takes some seriously clever chemistry and engineering.
So how do you do it? Well, the leading idea is a process called electrochemical CO₂ reduction, or ECR for short. The concept is pretty straightforward, actually. You use electricity, and hopefully that's clean, renewable electricity, to zap the CO₂, break it apart, and then rebuild its atoms into new, more valuable molecules.
Now, the very first attempts to do this, decades ago, used a device called an H-cell, and it's about as basic a setup as you can get. You just take 2 chambers of water, put a membrane in between, and then literally bubble CO₂ gas through the liquid on one side, where your catalyst is just waiting to work its magic.
But this simple approach hit a massive roadblock. See, CO₂ is terrible at dissolving in water. Just awful. So you get this traffic jam right where you need the action. The catalyst is hungry, it's gobbling up the few CO₂ molecules nearby, but the new ones just can't get there fast enough through the water. This bottleneck, which scientists call a mass transport limitation, meant the whole process was way too slow for any real-world use.
So that limitation sends everyone back to the drawing board. They realized the problem wasn't just about finding a better catalyst. It was about designing a better box. The whole next wave of innovation was focused on one thing. How do we get more CO₂ to the reaction site and get it there faster? And the breakthrough was a brilliant piece of hardware called the gas diffusion electrode, or GDE. The best way to think about it is like a high-tech sponge. It's porous, it's conductive, and it lets you feed CO₂ gas directly to the catalyst. It completely bypasses that whole problem of trying to dissolve it in water first. And the effect of this was just mind-blowing. By delivering CO₂ as a gas, instead of a dissolved liquid, the GDE cuts the distance a molecule has to travel by 1,000 times. 1,000! The journey shrinks from about 50 micrometers all the way down to just 50 nanometers. This was a total game changer for speeding up the reaction. Now, with this powerful new GDE, the field kind of split into 2 main designs. On one hand, you have flow cells. They use a flowing liquid to constantly deliver fresh stuff and wash away the products, which is great for controlled lab experiments. But for the big leagues, for industry, the favorite is the membrane electrode assembly, or MEA. This is a super compact, zero-gap design that slams the electrodes right up against the membrane. This slashes electrical resistance and really cranks up the efficiency. Okay, so let's just quickly recap that journey. We started with the simple H-cell, but it was just too slow. Then came the flow cell, which got the CO₂ there much better, but had this annoying tendency to flood. And that led us to the MEA, which gives us the high speed we need for industry, but it's a bit more complex and can get clogged up with salt. You can see how each step is a trade-off, right? A new solution with its own new challenges. And that brings us right up to today. We've got these amazing designs that work beautifully on a lab bench, but taking them from the lab to the real world, where you're processing millions of tons of CO₂, well, that's a whole different ballgame with a whole new set of hurdles. For this technology to be more than just a cool science experiment, it has to make economic sense. And to do that, the entire field is chasing one magic number, a current density of over 200 milliamps per square centimeter. That's the bar. You hit that, and suddenly this starts to look like a real competitive business. So what's stopping us? Well, it's a few really tough practical problems. That GDE can still get flooded.
with liquid clogging up the works. The catalysts themselves can wear out over time, losing their punch. And then there's the big one. Real-world smokestack gas isn't pure CO2. It's a dirty mix of stuff that can poison the whole system. On top of all that, you can even lose some of your precious CO2 to unwanted side reactions, which just tanks your efficiency. But here's the exciting part. For every single one of those problems, researchers are cooking up a new wave of brilliant innovations. The field is moving so fast, with solutions popping up that are designed to tackle these exact hurdles head-on. Let me tell you about 3 of the most promising ideas. First, engineers are building systems that can handle that dirty flue gas directly. This would skip the hugely expensive step of cleaning the CO2 first. Second, they're developing advanced membranes called bipolar membranes that give you surgical control over the chemistry right at the catalyst, which can boost efficiency and stop that CO2 loss. And third, there's this really elegant idea called cascade catalysis. It's a 2-step process. One reactor efficiently turns CO2 into a simple molecule like carbon monoxide, and then a second specialized reactor turns that into complex, high-value fuels like ethanol. So even with all this incredible innovation, if you ask anyone in the field what the single biggest remaining challenge is, they'll all tell you the same thing: stability, making it last. Right now, a fancy lab system might run for 100 hours. Some pilot projects have pushed that to maybe 2,000 hours. But to be commercially viable, a plant needs to run for over 20,000 hours. Closing that huge gap, that is the final frontier. And that brings us right back to the big question we started with. The science is moving at a blistering pace. The engineering hurdles, as tough as they are being knocked down one by one. The idea of taking our biggest pollution problem and turning it into a valuable resource, it's not a fantasy anymore. It's becoming a tangible, achievable goal. So the question isn't really if this can be done. It's when.